So welcome to segment 2 of a molecular view of reactions in aqueous solutions, and we were just starting to get into the actual equations of ionic reactions. We're looking at the molecular view, and next we're going to switch over and start to look at the actual reactions themselves. So here's an equation for an ionic reaction. We're going to take that lead nitrate, we're going to mix it with potassium iodide. We're going to see how it changed colors, but we're also looking now at the particles themselves. So when we had this in solution, we had lead and nitrate surrounded in water. We have potassium and iodide surrounded in water. And when we mix the two together, ionically or molecularly, what you're looking at is that the lead and the iodine are coming together and forming an actual structure. Okay? So when two soluble ionic solutions are mixed, sometimes an insoluble solid will form. Now, there are three types of equations we use to describe those styles of reactions. The first would be a molecular equation. That's pretty much what we've seen up till now, right? So the substances are all listed as complete formulas, and everything's kind of put out there, right? So it would be very much like just adding our symbols here, right? So we would say this and this are reacting to form that, okay? So the next type we're going to see is an ionic equation. Now here, all the soluble substances are going to be broken into their ions, and that's more like what was on the previous slide. Because we had the lead 2 there, I could put some plus signs in. So really, what you're looking at is not only we have this plus sign telling us we have these two things mixed together, but now we're going to put in some additional plus signs. We're going to put the plus signs in that go with the ions themselves. Not sure why that's not able to write over there, but it's not. It would be this. There it goes. There's a plus sign there. All right. And then the last thing we'll look at is the net ionic equation. And now this is only going to list something where there's actually a reaction taking place. So simply because I take two ionic solutions and I mix them together, that doesn't mean we're going to have a net ionic equation. Now we can have an ionic equation, but what we'll see is all the ions will cancel out because none of them will form anything, and now they're on both sides of the equation. So equations, ionic reactions then, for the molecular equation, you'll have everything listed off there. Right? The formulas will be written with the ions actually together. So it'd be the lead and the nitrate together still, the potassium and the iodide together still. Okay? It does not indicate the presence of ions. So it's not showing you that there's any ions whatsoever. And it does give identities to all the compounds. And again, these are good for planning the experiments or writing out just a basic equation. Okay? So again, there's our lead nitrate. It's in aqueous solution. We're going to mix it with the potassium iodide that's in solution. It's going to form lead iodide and potassium nitrate. Now, equations of the ionic reactions, what we're going to do is emphasize the reaction between the ions. So now we're going to expose those electrolytes, show the dissociation and how they're going to break apart. Okay, so we'll use these to visualize what is actually occurring in the solution. Now remember, all these things are happening at the same time. So if I've already put the potassium iodide in solution, then the particles are already broken apart. And so now it's just a matter of mixing them together. Okay, and soluble solids will be written together as they don't dissociate. So if I get two ions that are in solution that form a compound that is insoluble, then we'll write that as a solid. So our ionic equation then will take up a lot more space because it's all broken apart. Instead of having the lead nitrate together, now we have the lead indicating its charge is a +2. It's in an aqueous solution, and then the nitrate is going to form two nitrates. And that's going to be also in an aqueous solution. We'll do all of that for all the different ionic compounds, except for notice the lead iodide is going to form a precipitate. So we're going to mark that as a solid, and we're going to keep those together. All right, so equations of ionic reactions then. The last step is going to take into account the spectator ions. Now, spectator ions simply means that they're not doing anything in the reaction. Okay, they don't take part. They're just kind of watching things, like the potassium and the nitrate in our example here. They're on both sides of the equation. So our net ionic equation is going to eliminate all spectator ions. So anything that's on both sides, both the reactants and the products, if I can find it on both sides, I'm going to cancel them out, and I'm not going to write them in the net ionic equation. So here, we're going to emphasize the actual reaction itself. Okay, so we're going to focus on what's actually changing. And so remember we had the nitrate and we had the potassium, but they were on ions on both sides. We're going to cancel those out, and then what we're left with is simply the lead plus the iodine to make the lead iodide. Okay, so that was our net ionic equation. Now, criteria for ionic and net ionic equations: materials have to be balanced. Okay, you have the same number of each kind of atom must be present on both sides. That has not changed. You also have to have an electrical balance. So we have to make sure we have the same number of cations on the same side as the other side and the same number of anions. So there has to be a no net electrical charge on the reactants. Okay, so at the end of the day, all the charges have to balance on both sides as well. Now, that charge does not have to be zero. Okay, the charge does not have to be zero. Little caveat there. Okay, both sides have to be -1. If one side's -1, the other side has to be -1. That can happen. Okay, so it doesn't have to be 0 on reactant side, 0 on product side. It could be +5 on the reactant side. If it's +5 on the reactant side, what has to be true? It has to be +5 on the product side as well. All right, so let's take a look at this then. Which of the following is not electrically balanced? Electrically balanced. Okay, so the way we'll do that is here we see we have silver with a +1, chlorine with a -1. That gives me a total of 0. On the product side, it's a neutral compound, it's 0. That's electrically balanced. Here we have a +1 for the ammonium, a 0 for the water, a 0 for the ammonia, +1 for what we call the hydronium. And so that means we have +1 on both sides. That means it's balanced. Okay, so go ahead and check out the other three. Obviously, the answer is now either C, D, or E. Give you a second. And hopefully you figured out that it was D. So D, we have a +1 for the magnesium. Realistically, it was probably a typo, but it's listed as a +1. We have a -2 for the 2 hydroxides. That gives us a total of -1. And over here we have 0. So that does not balance. All right, give it a try again here. Pause. All right, hopefully you picked C. C, we can see we have a -1 here. We have +2 and a 0. So -1 does not equate to a +2. All right, so back to those net ionic equations. Now there's many ways to make lead iodide. Okay, so if I start with this reaction, I have lead nitrate plus potassium iodide. That's the one we were just looking at. However, I could take lead acetate and mix it with ammonium iodide. Both of those are soluble, but when they mix together, they both will produce lead iodide. So we have different starting reagents. However, at the end of the day, they both have the same net ionic equation. Okay, in the first one, we know that the nitrate will cancel out with the nitrate. Potassium will cancel out with potassium. We're going to see that same thing in the second reaction. The acetates are going to check out, and the ammoniums are going to check out, which means we end up with the same equation, the same, I should say, net ionic equation. And if we mix those two reactions together, we see the same yellow solid. Okay, same yellow solid. All right, so converting molecular equations to ionic equations, that's where those electrolytes come into play. Strong electrolytes exist as dissociated ions in solution. So the strategy is identify your strong electrolytes. This way you can use the subscripts as coefficients to determine the total number of each type of ion. Right? Since it's a strong electrolyte, you know it's going to completely break apart, and those subscripts can become coefficients. Separate ions in all strong electrolytes. Show states as recorded in molecular equations. All right, so let's write the correct ionic equation for each of the following. So here's lead nitrate plus ammonium iodate. It's going to form lead iodate plus ammonium nitrate. So I'll give you a second there. And so you get lead 2 plus 2 nitrates, plus 2 ammoniums, plus 2 iodates. Gives us the lead iodate as a solid, plus the ammoniums, plus the nitrates. How about sodium chloride plus mercury nitrate? And here we know that the sodium nitrate is going to go into solution, but the mercury chloride is going to be produced. And so we're going to break all those other things apart into their different ionic pieces. All right, so let's consider this reaction. Sodium sulfate plus barium chloride goes to sodium chloride plus barium sulfate. Write the correct ionic equation. So A, B, C, D, or E. Write the correct ionic equation. I believe they want the net ionic equation here. So what is the correct net ionic equation? And hopefully you came up with D. Okay, so that's the net ionic equation. Let's see, do any of them come up to be the right ionic equation? So we have 2 sodiums, 1 sulfate, 1 barium. Okay, so this one's out because that does not exist as an ion. So it can't be that one. We have 2 sodiums, a sulfate, a barium, the 2 chlorides. Got that part right. 2 sodiums, 2 chlorides, 1 barium sulfate. Yeah, so you might have chose B based upon the actual question they asked first. All right, that's why I wanted to clarify, because I knew we wanted the net ionic equation, not just the ionic equation. And there's 2 sodiums, a sulfate, barium. Oh, there's those Cl2s again, so that one's out. And then barium plus sulfate gives barium sulfate. Yeah, and here we know these two form solids, so that can't be it. All right. So converting ionic equations to net ionic equations, your strategy here, identify your spectator ions. Then you can just cancel them from both sides, and then you'll just rewrite the equation using only substances that actually react. This will show states as recorded in a molecular and ionic equation. So write the correct net ionic equation for each. So now we're going to take lead nitrate plus potassium iodate. It's going to form potassium or lead iodate and then leave us with potassium nitrate. So here what we're going to see is that we can cancel things out, right? So we have 2 nitrates that are going to cancel out here. They're also going to cancel out on the product side over here. We have 2 potassiums that are going to cancel out with 2 potassiums on the product side. Then what we'll do is just rewrite the whole thing. So we have lead 2 plus, and we'll keep the things we didn't cancel out, plus 2 IO3s produces the precipitate plus nothing else. Everything else got canceled out. Okay. So again, you'll just identify those spectator ions that are on both sides of the equation, cancel them out, and then rewrite your equation without them. So we have sodium chloride plus mercury nitrate produces sodium nitrate and mercury chloride. So again, we'll cancel the sodiums out, we'll cancel the nitrates out. Also, I want to point out the coefficients have to line up, right? Now, if we have a balanced equation, this shouldn't be a problem. As long as we have a balanced equation, you should have 2 sodiums on both sides anyway. They should cancel out. All right. All right, so consider this following molecular equation. Write the correct net ionic equation. And hopefully you selected A. Okay. Now, criteria for balancing ionic and net ionic equations. First, we do a material balance. Right, there must be the same number of atoms. That's just like we saw before. The new piece will be the electrical balance. So when we're looking at net ionic equations, we could have a charge balance that's not 0, but it does have to be the same on both sides. Okay, so to be electrically balanced, they both have to have the same charge, but it just means that charge doesn't have to be 0. All right, so learning check for balancing equations for mass and charge. Balance the molecular equation for mass. So if this is our reaction, then of course we'll keep those polyatomic ions together and we'll simply balance it like we normally would. Now to balance the ionic equation, what we'll do is look at all the charged pieces here and make sure all the charges are adding up. So here we have a plus 6, right? Because I've got 6 with a plus 1. I've got 2 minus 3, so that's going to be a minus 6. I got 3 times 2, another plus 6. And then 6 times minus 1 is a negative 6. So overall, we've got plus 6 minus 6, 0, plus 6 minus 6, 0. So the reactants total, a 0. For the products, we have 6 plus, so plus 6. We have 6 minus, a minus 6, plus a 0. So plus 6 minus 6, again, the product side is also a 0. So these two then are charge balanced. Okay, so again, in this case, your charges have to end up to 0. Now, your net ionic equation should then be balanced for mass and charge. Okay, so if the molecular equation is balanced and charged, and then the ionic equation is going to be balanced for charge, so will the net ionic equation. So here we have 3 times 2 gives us a plus 6. 2 times a negative 3 gives us a minus 6. And on this side, we have 0. So there it is. Simple as that. All right, we're going to end segment 2 here. And in segment 3, we're going to turn our attention to acids and bases.